Welcome everyone. During this lecture we'll introduce the normal force, we'll introduce the field of physics known as dynamics, and we'll also introduce a basic dynamics application. Let's begin with the definition of the normal force. Whenever two or more surfaces are in direct contact with one another, the force exerted upon surface A by surface B and vice versa will be directed in a perpendicular fashion with respect to the surfaces. This force is called the normal force. And we abbreviate it with N. Small case n. Let's discuss several examples. For instance, let's assume that we have a block that's in direct contact with the floor. And so we have two surfaces that are directly in contact with one another. And the question is, what will be the nature of the normal force between the floor and the block? Let's talk about the force that the floor exerts upon the block. It turns out that the floor exerts a normal force that's directed upward against the block, and we would represent that in a free body diagram like this. That's the normal force, and we label it with the letter N. In this example, we have someone climbing a hill. The surfaces that we're interested in are, of course, the surface of the hill and the shoes. The hill will exert a normal force against each of the soles of the shoes, and that force will be directed in a perpendicular fashion. So if we drew the hiker again, there are two normal forces, and they would look like this. We can call this normal force N1, and we can call this normal force N2. Let's now imagine a block being pushed across a ceiling. So there's our ceiling, and the crosshatch marks indicate a stationary surface. We have a block that looks like this, And we're going to apply a force like this in order to push the block against the ceiling. Well, the ceiling will react to the top surface of this block by exerting a normal force, and the direction of that normal force will be downward. And so in our free body diagram, the normal force exerted by the ceiling on the block would look like this. We will now introduce the branch of physics known as dynamics. Dynamics is the branch of physics which relates the forces acting upon an object to the object's resulting acceleration. This relationship is established through Newton's second law. Let's take a look at an application of dynamics. In this example, two blocks of masses 15 and 30 kilograms are connected by light string as shown below. If the system starts from rest and the surfaces are frictionless, we'll begin by drawing a free body diagram for M1. We'll determine the normal force applied to M1. We'll determine the relationship between the tension and the acceleration by applying Newton's second law. We'll draw a free body diagram for M2. We'll determine the relationship between the tension and the acceleration by applying Newton's second law. We will solve for the tension and the acceleration, and then we'll determine the system's velocity just before M2 reaches the floor. Let's take a look at the diagram. So this is the diagram that represents everything we just read. We have two masses. Notice that one of them is on a tabletop and there's no friction. In other words, the surfaces are very slippery and very smooth between the block and the table. This mass is connected with a string to another one, M2, which is kind of dangling from the edge of the table. This is a frictionless pulley over which the string is rolling. And M2 is right now at a height of 1.5 meters above the floor. Later on, we'll determine how fast it's traveling just before it reaches the floor. So let's begin by drawing a free body diagram for this first mass. So here's our 15 kilogram mass. We're isolating it from the rest of the system, and can you think of a force that's acting on this block? Here's the block. And the first thing we note is that the block has weight. In other words, the earth is pulling at it in a downward fashion, and so we'll represent the weight with this arrow. The weight, of course, just equals mass times gravity. That's 15 times 9.8, and that equals 147 newtons. Of course, the 9.8 is the value of gravitational acceleration. Also, the two surfaces, the tabletop and the bottom of the block, are in direct contact with one another. That means that the table will exert a normal force that's directed upwards against that block. We can represent the normal force like this. The block is connected to a string, and that string is pulling the block towards the right with a tension. We can represent the tension like so, and that tension will create an acceleration directed to the right. So the acceleration could be represented with an open arrow. The reason, again, we use an open arrow is because we want to distinguish between acceleration and all the other forces. In part B, we want to determine the value of this normal force, and we will do that by applying Newton's second law. Now, we have a choice to make on the right-hand side of Newton's second law. In other words, after we sum the forces, and by the way, we'll be summing the forces in the y direction because the normal is directed along the y-axis. When we sum the forces in the y direction, we have to choose whether that sum equals 0, positive ma, or minus ma. So how do we make that selection? Well, we will examine our diagram, which is right here, and we'll note that there is no acceleration along the y-axis. The acceleration we drew is directed along the x-axis, and because of that, we will choose 0 on the right-hand side of Newton's second law. In other words, the object is considered to be in static equilibrium along the y direction, and that's because it's only accelerating along the x direction. So 0 is our choice, and therefore our guiding equation is sum of the forces in the y equals 0. And now the question is, how many forces are directed along the y-axis? And by examining our free body diagram, we note that there are only two. The normal is directed along y, the weight is directed along y, the tension, of course, is directed along x, and the acceleration is not a force. So we'll extend 2 fingers from that summation, and we'll incorporate the normal as a positive force because it's directed upward, and the weight will be incorporated as a negative force because it's directed downward. If we add those 2 forces, we should get 0. We calculated the weight. The value is 147 newtons. We'll transfer that to the other side, and as a result, the normal equals 147 newtons. So what we're finding is that if the object weighs 147 newtons, then the table will push back up against the object with an equal force, namely 147 newtons. That's not always the case, but it is under these circumstances. In part C, we want to find the relationship between the acceleration and the tension by applying Newton's second law. So let's apply Newton's second law. Of course, the tension is directed along the x-axis, as is the acceleration. And so we will apply the second law as the sum of the forces in the x, and we have that choice to make: 0, ma, or minus ma. Our diagram guides us to choose positive ma because the acceleration is directed along the positive x-axis. So ma is our choice. And so our guiding equation is just the sum of the forces in the x must equal ma. How many forces are directed along the x-axis? Let's look at our diagram. We only have one, and that is the tension. Keep in mind, acceleration is not a force. On the left-hand side, we're only accounting for forces. So we'll include just the tension on the left-hand side. And therefore, the tension will equal MA. If we substitute 15 kilograms for the mass, this is the resulting relationship, and at this point we cannot solve for the tension or the acceleration. Let's label this equation as equation number 1 and move on with our analysis. In part D, we will draw a free body diagram. For M2. Let's take a look at M2. M2 is the suspended mass, and the first thing that we note is the fact that it has weight. Any object with a mass always has weight. That's because the Earth is tugging down on this object. Let's represent the weight. So here's the weight vector. Like before, the weight equals mg, which is mass times gravitational acceleration. The mass in this case is 30. G is always 9.8. And that results in a weight of 294 newtons. Now in this case, there is no normal force because this block is not in contact with any other surface. Now it is in contact with this cable, but it's not touching any other surface. There is no normal force for M2. Now we have to represent the reaction between the string and the block, and of course the string exerts a tension, and that tension is directed upward. And so we can represent the string's tension with this vector. This block will have an acceleration. It's going to accelerate in a downward sense, and so we can represent that acceleration with a downward arrow. And that is the complete free body diagram for mass 2. Let's move on to part E. In part E, we want to determine the relationship between the tension and the acceleration. And we'll do that by applying Newton's second law along the y-axis, because notice that the forces and the acceleration are directed purely along y. So we will lay out Newton's second law for the y direction, and we have a choice once again to make, which is, does the right-hand side equal 0, ma, or minus ma? Well, our free body diagram guides the choice. We have noted that the acceleration is directed downwards. Downwards considered a negative direction, and therefore we will choose negative ma. How many fingers will be extending from the summation? Well, we need one for every force in the y direction. Look at our free body diagram and note that we have two forces along the y-axis, the tension and the weight. Keep in mind, once again, that acceleration is not a force. The acceleration is accounted for on the right-hand side. So we only need two forces on the left-hand side. We'll extend two fingers from the summation. The tension goes in as a positive force, and the weight goes in as a negative force because downward is considered to be a negative direction. And there's our guiding equation. So from this we have the tension minus 294 equals minus ma. In this case the mass equals 30. And the best we can do right now is to clean up this equation by transferring the 294 to the other side. If we do that, the equation becomes positive 294, right? Because we have to change the sign, minus 30a. That's as far as we can take this. And so we'll place this result in a box and call this equation number 2. And now we can apply algebraic strategies towards the solution of the acceleration and the tension. So in part F, we want to solve for acceleration and the tension. And here's how we can go about doing that. We have two equations. Let's just recall them. So let's recall equation 1. And equation 1 looks like this. Here it is. T equals 15a. Let's bring that onto the page. So once again, T equals 15a, and what we can do now to solve for acceleration is to substitute the 15a instead of t within equation number 2. So instead of the t, we'll substitute 15a. That'll produce 15a equals 294 minus 30a. We'll bring the 30a over to the left-hand side and note that it becomes positive. And so we have 30a plus 15a. That results in 45a equals 294. Next, we'll divide both sides by 45. And the result becomes 6.533. And of course, the units for acceleration are meters per second squared. In the last part of the problem, in part G, we want to determine the object's velocity. We'll call it the system's velocity. Just before M2 reaches the floor. Well, let's take inventory of what is known. First of all, we just determined the acceleration. It has a value of 6.533 meters per second squared. We also note that in the original text, the system starts from rest. So that means V0 equals 0. And we know something else. Let's take a look at the diagram. We know that mass 2 travels a distance of 1.5 meters by the time it reaches the floor. And therefore, we can introduce an x value of 1.5 meters. Now I know that this mass is traveling along the y-axis, but we'll introduce that value as x within our motion in 1D equations. Okay, so x equals 1.5 meters, and now we need to look at our 1D motion equations and find an equation that will solve for the final velocity. So here are the equations that we've established earlier, the one-dimensional motion with constant acceleration equations, and let's try to determine which equation will assist us. The first equation won't work, and that's because we're trying to find the velocity, but we don't have the time. Second equation doesn't have a velocity. Of course, the symbol for velocity is just v. The third one does, but we don't have knowledge of the average velocity. The fourth equation won't work either because we don't know the time. The fifth equation seems to work. We're looking for velocity, which is v. We have the initial velocity right here. We have the acceleration known, and we have the value of x known as well. So let's apply this equation. Okay, so the original or the initial velocity is 0. The acceleration is 6.533. The value for x is 1.5. If we multiply those two, we get 19.6. Next, we have to take the square root of both sides. And in doing so, we have to introduce a plus or a minus. In this case, we're going to choose a minus sign because we know that the mass is traveling downwards along the y-axis. And so the velocity just equals the negative square root of 19.6, which equals negative 4.427. And of course, the units for velocity are meters per second. And by the way, that will be the velocity of the entire system because the two blocks are connected through a string. So whatever acceleration m1 has, m2 will have the same acceleration as well, and same goes for the relative speeds. And that concludes this lecture.